to apologize in advance because you're going to be hearing my pen click on the screen. Usually I do these recordings at home, no, at school, but today I'm at home and don't have my microphone. I probably shouldn't have told you that my pen will be clicking because now you'll listen for it. So my apologies. You can just, ignore that if you want. Last video, we discussed function notation, where if you have a function like f of x, you can plug a number in for x and calculate the output. So we have an input of 4 and an output of 12 if our function was 5x minus 8. Remember, f of x just means y. And we've talked about functions, how they can be written as maps, rules, which means equation, tables, and graphs. Today we're going to do function operations. Operation just means add, subtract, and multiply. There's also divide, there's power, there's, just things we do for calculations. Those are operations. There's other ones besides those main four. We're going to save division for another time. I think I talked about this before, but division is funny. With addition, you tend to get whole numbers out of whole numbers. In subtraction, you'll get whole numbers out of whole numbers, or at least integers. In multiplication, you'll get whole numbers out of whole numbers. But with division, you don't. So division is kind of special. That's why we treat it differently as such. Okay. I have two graphs here that I just made up. A graph on the left shows how... So the two graphs are for husband and wife. We can call them Joe and Susie, or whatever we want. The graph on the left shows how much money a husband has every month. So in month 1 here, he has $7,000. This is the point, 1 comma 7,000. That means in January he had 7,000. And in March, he also had 7,000. Because that's month 3. This would be 3 comma 7,000, not 1. This graph is a function. I talked briefly in a previous video about the vertical line test. The graph passes the vertical line test. There's no point at which a vertical line hits the graph more than once, which means we have a function, which makes sense. Joe can only have one amount of money. It's not like he can have two different amounts at the same time. So we can see that Joe starts out at 7,000, then he spends 2,000 a month. It's going $2,000 every month for a couple months. Then he sits at 1,000 for a while, and then gains 1,000 a month. This is Joe's function. Over here is Susie's function. She starts at 1 comma 2,000, and she is steadily gaining 1,000 a month, and then she plateaus and lays off for a while. Each of these functions don't have any sort of rule. There's no way that I could write some function as an equation that's going to get me from month to amount of money. That's okay, it's just there's no rule that exists for these functions. That one that I wrote doesn't work for this. Well, suppose that, even though Joe and Susie have separate bank accounts, they still think of their money collectively. They still pool it together and say, together we have, X dollars. That means we could add this graph to this graph and put their monies together. That's kind of tough to do. Not tough, just tedious. It's very simple, but it's tedious. We would have to, at each month, add up their two totals. For example, here, this was 7,000, and in month 1 over here was 2,000. So in month 1 together, I'm going to say down here is both of them together. Here's their combined money. In month 1, they would have 9,000. And I'm going to put all these together. So here, this was also 7,000, and this was 3,000. So in month 2, they had 10,000. And here was 7,000, and here was 4,000. So in month 3, they had 11,000. Notice how this is going up by 1,000 a month, just like how this was going up by 1,000 a month, because this was flat. This wasn't changing. But now this is going to start going down. And this is going down by more than this is going up. In this month's span, it went up by 1,000. But in this month's span, it went down by 2,000. So if I take 5,000 and 5,000, put them together, we drop back down to 10. Then it's going to drop again to 9, and again to 8. Now, Joe levels off. He doesn't make any money for a while. She makes 2,000 for a couple months, 1,000 a month for 2 months. So So we're going to gain 1,000. And I've kind of lost track of where I am. So let's see here. This was month 8. So I've already done month 8 here and month 8 here. Let's look at month 9. In month 9, Susie has 9,000. Joe has 1,000. So in month 9, they're at 10. Yeah, they both stayed flat. They stay at 10. In month 10, it's going to be 9,000 plus 1,000 again. And then in 11 and 12, Joe starts peaking up again. Okay, let's call this function here. Let's call this function j of x. J for Susie. We could call it f of x if we wanted to, but I'm going to use j for Joe, not for Susie, because I'm not crazy. J for Joe. J of x, f of x, it's all the same thing. We can use any letter we want to make a function. Let's call this function s of x. S for Susie. Here's Joe's function. Here's Susie's function. Well, this graph here we could call j of x plus s of x. Two functions added together. And we can see how this is their combined bank account. It's going up when she's making money. It's going down when he's spending money. It plateaus when they both don't make any money. It makes pretty good sense, actually. That was us adding two functions from a graph. What might have been easier would have been to add them from a table. Sorry for the different looking screen. I had to fix a mistake I made on a table. Over here I have tables, believe it or not, that had a mistake on them but don't anymore. This first table is Joe's money. The second table is Susie's money. Adding these points up by graph, we had to check each point on the graph. What probably would have been a bit simpler is if we'd just taken the points and written them down, and we know the x value is month, like this stands for months, and the y value is going to be total combined money they have. The y value is individual money, we put them together. In month 1, they had 9,000. In month 2, they had 10,000. And then in month 3 it was 11. 7 plus 4 is 11. And adding up all these points, I don't want to write down all the zeros every time, gets pretty simple. Notice how I'm adding up the y column, okay? The y columns are adding, but the x columns are not. Like here, I'm going to add up this 1,000 and this 8,000 to get 9,000, but I didn't add up the two 7s to get 14, because that wouldn't make any sense. It's not like they doubled their months. They just increased their money, but they didn't increase their inputs. When you're adding up functions, the inputs don't combine, just the outputs, just the y values. In month 8, they had 9,000. In month 9, they had 9,000. In month 10, they had 9,000. In month 11, they had 10,000. And in month 12, they had 11,000. They ended up at their highest point. Matching this one here. Way to go, Joe and Susie, you did it. This would be the table for j of x plus s of x. It is still a function. If you take two functions and add them together, you're going to get another function. Okay, so that was us dealing with graphs and tables. Next, let's talk about rules, which are also equations. So the previous functions didn't have a rule, so there's no equation to get us from the inputs to the outputs. But here are four equations that do have, or four functions that do have rules. We call them f of x, g of x, h of x, and k of x. We just use different letters like different labels. Instead of calling this equation Frank, instead of calling this equation Grant, and this one Hector, and this one Kyla, we call them f, g, h, k. They're just labels. Well, this is saying take the f function and take the g function, add them together. The f function is 3x plus 8. The g function is negative 2x minus 5. So I get x plus 3. If you're not sure how I got that, if the parentheses are kind of confusing you, always start these with parentheses, but the way you get rid of parentheses is by distribution, and there's nothing to distribute here, so this just becomes 3x plus 8 minus 2x minus 5, because plus and negative becomes minus. Then I combine my like terms. So I'm doing 3x minus 2x, which is 1x. and 8 minus 5, which is 3. So we end up with x plus 3. Now be really careful with subtraction. There's a very common mistake that happens in subtraction we got to be on top of. I'm again doing f and g, but I'm subtracting them. So that's 3x plus 8 minus 2x minus 5. And remember how I said you get rid of parentheses with distribution? It's like here we distribute a 1 and we just stay 3x plus 8. But here we distribute a negative 1 and we get negative 2x plus 5. And this plus 5 is a very big deal. It's a very common mistake to miss that. We have to distribute the negative to get rid of the parentheses, and that causes everything positive to be negative and everything negative to be positive. Now I combine my like terms. 3x minus 2x is 1x. Positive 8, that's plus 8 right there. Positive 8 plus 5 is 13. This ended up being x plus 13 as opposed to x plus 3. There's f plus g and f minus g. So I'll do a few more examples of subtraction just to kind of help us get a feel for it. I'm going to do g minus h. So that's negative 2x minus 5 minus 6x plus 1. Distribute to get rid of your parentheses. Negative 2x minus 6x is negative 8x. Negative 5 minus 1 is negative 6. So g of x minus h of x is negative 8x minus 6. Okay, try to do k minus h on your own. Pause it real quick and do it. Then check my work. K of x is 4x. H of x is 6x plus 1. 4x minus 6x minus 1 is negative 2x minus 1. If you're asking where this minus come from, it came from distributing this negative. Same with this minus right here. Okay, next is multiplication. You know how to do this. You've multiplied expressions before. I'm doing f times g. So it's going to be 3x plus 8 times negative 2x minus 5. Distribute the 3x to get negative 6x squared. Distribute the negative 5 to get negative 15x. Distribute 8 to negative 2x and you get negative 16x. And then 8 times negative 5 is negative 40. This becomes negative 6x squared minus 31x minus 40. I combined these like terms in the middle. Negative 15x minus 16x is negative 31x. Okay, so if that felt like a lot that was real fast, I can talk through it again. If it didn't, you can fast forward, a few seconds probably. But I'm doing this 3x is multiplying to each of these terms. So 3x times negative 2x is negative 6x squared. Here. 3x times negative 5 is negative 15x. 8 times negative 2x is negative 16x. And positive 8 times negative 5 is negative 40. Then combine the like terms in the middle, and you get this. Try and do the last two problems on your own. Pause it and try them. G of x times h of x is going to become negative 12x squared minus 2x minus 30x minus 5. The middle terms can combine because they're like terms. Negative 12x squared minus 32x minus 5. Finally, we have h of x times itself. This is h of x times h of x. 6x times 6x is 36x squared. 6x times 1 is 6x. 1 times 6x is 6x. 1 times 1 is 1. Saying 6x, 6x, 6x over and over again kind of sounds like that word success, That's the word I'm sure you thought I was saying over and over. Boom. Middle terms combine. There is h of x times itself. We could take take h of x times h of x and actually write it as h of x squared. Something times itself is something squared. Success. Okay, to recap, functions can be added, subtracted, multiplied, and divided just like numbers. If you have a function rule, the operations are quite straightforward. A function rule means an equation. You just add, subtract, or multiply. This is the word given. If given only a graph or table, it must be done for each individual point. That was the first example with people's money. If you're given a graph or a table, add up the add up the outputs from each input. Add up the y points for each x put. Add up the y values, not the x's. Way to go. Big old green check. You should be proud. I know I am.